Hello, can you hear me? Okay, let's wait for 2 more minutes. Okay. Can you see my iPad? If you can see it, say yes. Okay, that's good. Okay, let's get started. I'm just going to recap what Cho had talked this morning. So we are going to talk about transformer model in this lab. So so we know we've been talking about RNN in the previous lab, and we know that in RNN we input the words sequentially one by one, and then we get the output. Okay, and there's this like recurrence connection between each input, so like they are dependent on the previous input, and so on. So in terms of computational time, since we have to input sequentially, it takes time. And then there might be some, so how do we get rid of this recurrent dependency between the input? So if we get rid of recurrent dependency, it is going to look like this. So transformer is like this. So, but if we do this, if we get rid of recurrent dependency, how do we represent the relation between words? Because in natural language, words are like have some relation to each other. For example, subject and verb have relation, verb and object has relation, and so on. So how do we encode this kind of relation and dependencies in transformer? So to do that, transformer use something called self-attention mechanism, which is basically to get the encoding for each word, you are going to attend to other words and also itself in the sentence. So this is called self-attention mechanism, which means that you are using attention mechanism on the sentence itself. Okay, so attending to itself. So it's called self-attention mechanism. So I will going to explain the attention mechanism later again, but it is very similar to the attention mechanism that we use in machine translation. Okay, so yeah, so another thing is since in RNN we put in the input sequentially, so the RNN know the sequential word order, and the word order can be important in natural language processing, right? So the question is, how do we encode the word order in transformer? So Cho mentioned this in this morning. So we can add something that encodes the position and to the model. So what we do is we add something called positional embedding. So this is the position 1. So we are going to get the embedding for position 1, position 2, position 3, and so on until the position n. And we are going to add this positional embedding to the normal word embedding to get the input embedding, okay? So there are a few ways to do to define the positional embedding. One way is to define it in the same way as the word embedding and land it during the training stage. But what if like our sentences are very long? So the positional embedding vocabulary is going to explode. Okay. So is there other ways to do that? Is there other way to tell the model a sense of position? So in this transformer architecture, they use something called, they use sine function and cosine function as positional encoding. So I will also explain more details about this positional encoding later in the lab. So yeah, let's continue to the next step. So when transformer was first introduced, it was introduced as a neural machine transition model, although these days we use transformer. So initially it was introduced as sequence-to-sequence model, but these days we use transformer without sequence-to-sequence, just like encoder architecture for language modeling and so on. So the initial transformer model introduction consists of an encoder and decoder, just like you learned in the previous lab. So, and if we take the closer look inside this encoder, it contains 6 identical layers. So like 1, 2, 3 to n. So n equal to 6 in their introduction. And for the decoder layer also, it contains a 6 identical layer. So 1, 2, 3 to n equal to 6 identical layer. So, and the input is going to be the word embedding. For example, if our sentence is I am Pooh, we are going to use the input embedding, word embedding for I, word embedding for n, and word embedding for Pooh. And we are also going to add this embedding with positional embedding. So position 1, position 2, and position 3. And then the input, so input W1, W2, W3. Input W1 is going to be P1 plus E1. W2 is going to be P2 plus E2. And W3 is going to be P3 plus E3. So this is going to be the input to the transformer. And it is going to go through 6 identical layers. And then we are going to use the output of the final layer as like a part of the input to the decoder. And then we are going to similarly use the input embedding with a positional embedding to the decoder layer, just like in LSTM or RNN. And then we are going to output the translation. So it is like very similar to RNN machine translation, just that you change the architecture of encoder and decoder to be transformer. Okay, so let's talk about the component of this specific layer. So what is the, I will explain about positional embedding later. So yeah, so let's look at this encoder layer. What is inside this encoder layer? So inside encoder layer, it has 2 sublayers. So the first sublayer is called self-attention, which is going to find the relation. So if I have like 3 words input, I and Pooh, so it's going to find the relation between all the words using the self-attention. So this is a self-attention layer. And this is going to be a feed-forward layer. It is just to introduce the nonlinearity. So Cho also mentioned that in this morning lecture, okay? So if you look closely at this, so it is built like this. So the self-attention model here contain this layer and this layer. This layer is attention, which is the same as the attention mechanism from the previous lab. And I will also explain it again later. And it also contains add and normalize. What it does is, so let's say we have an output X from the self-attention layer. So it do a layer normalization to the output of self-attention layer. So we have like ACE1, and this is self-attention ACE1, and then add a layer normalization because it is known to help with web propagation, just like Cho mentioned in this morning lecture. And then it also add a residual connection for an ACE. So you add ACE here. So residual connection is also like to prevent the vanishing gradient issue in the web propagation. So, okay, so, but as we mentioned this morning, this is just a linear layer, and we want to introduce some nonlinearity. So we added a feed-forward with nonlinearity layer here. So this is the nonlinearity layer. So it's just a feed-forward net. And then we also do the residual connection and layer normalization again. So let's say this is going to be, let's say the input is C here. So it's going to be feed-forward network for C. And then we do layer normalization, and then we add C again. So this is like this two-step, okay? So this is only one layer of encoder. So this is only this one layer, and one layer contains two sub-layer, and we explain the two sub-layer here. Okay, is it clear so far? So before we continue to decoder, let's look at the code for encoder. So this is to install the packages that you need. So if you need to install it, you just remove the command and then run it. And we input the required packages. So far is fine. So like I mentioned, transformer is initially introduced as encoder-decoder model. It consists of an encoder and decoder, embedding for source side and embedding for target side. And this is just a generator to generate the decoding. So, and it consists of an identical layer of encoding layer and an identical layer of decoding layer. So I just explained that the encoder layer contains attention and layer normalization plus residual connection, feed-forward, and so on. So, and they have this identical block of this encoder layer in their transformer architecture. So we define something called clone, which is just to copy the encoder layer to for n identical time. In this case, n is going to be 6. Okay, so and we define encoder layer. So encoder layer contain layer. Layer is just one encoder layer copy 6 times, n time. Okay, and then we have a layer normalization at the end of the encoder. So this is just, so in the forward function, we are going to go through these identical layer in the self.layer that we define here. And then after we go through all the 6 layers, we are going to normalize again. And that's just the encoder. So this is what I just talked about. So, and this is just a function for creating the layer normalization. So you can look at it on your own later. It's just the layer normalization formula. So, and as I mentioned, there is like some residual connection and normalization, layer normalization connection in each sublayer. So to define this, we are going to define something called sublayer connection class. So sublayer connection, we define the layer normalization, which is known here. And then we are going to add the dropout to that output of the layer normalization, and then we add the residual connection there. So far it's like very intuitive, right? So after sublayer connection, we can define the encoder layer, which is going to be used as input to the encoder function. So how do we define the encoder layer? So encoder layer contain a self-attention layer, as we mentioned here, and a feed-forward neural net. So we define a self-attention layer, and we define a feed-forward neural net, and then we define the connection for residual layer and layer normalization using the sublayer connection class that we defined earlier. And then we, So we do the sublayer 0. The first sublayer is going to be self-attention layer. And sublayer 1, the second sublayer is going to be feed-forward layer. So this is how we get our encoder model. Okay, is it clear so far? Okay, I will move on to the decoder. So let's look at the iPad. So in the decoder layer, it has one addition. So this is the encoder layer that we talked about before. And decoder layer is very similar. It contains self-attention just like encoder. And it also contains a feed-forward network, just like the encoder. And it contains an additional layer called encoder decoder attention. So this is just like machine translation with RNN. What it does is it trying to attend to the output of the encoder to get the translation. Okay, so this is just encoder decoder attention that you have seen in the RNN attention lab. So if we take a closer look, so this is the encoder that we defined. So you don't really need to look at it right now. We have seen it. So in the decoder layer also, it contains self-attention, layer normalization with residual connection. And then the encoder decoder attention is going to use the input from the previous self-attention layer, as well as the input from the encoder output. And then we will perform the attention mechanism. So attention mechanism, if you remember, it is query and key, go through softmax. Yeah, go through softmax, and then do the normalization, and then multiplying with value. So I will talk in detail later. So yeah, so this is just one additional layer to attend to encoder output. So let's look at how to define this in the code. So similarly in decoder layer, we are going to have an identical layer of a decoder layer. So we are going to use the clone method to clone it n times. And then the output is going to go through a layer normalization. And then in our forward function, for each layer, we are going to go through each layer. So memory is going to be the hidden output from the encoder. And then X is going to be the input from the previous layer or input to the decoder. So, and we are going to go through this layer n times. And at the end, we are going to add a normalization, layer normalization. Okay, so yeah. So this is just explaining what I have said before, and like there is another sublayer that is going to do attention to the output of the encoder. Okay, okay. So in decoder layer, it contains a self-attention layer just like encoder, and then this is the attention layer for attending to the output of the encoder, and then a feed-forward layer, and then the sublayer connection between each sublayer, which is the layer normalization and residual connection. Okay, so we have three sublayer. Sublayer 0 is defined as self-attention. Sublayer 2 is attention to the encoder, and sublayer 3 is the feed-forward neural net. But in the decoder, so in the encoder, you can attend to every word in the input. Okay, so let me see. Let's look at the iPad. So in the, can you see the iPad? Say yes if you can. Okay, so let's say so in encoder, this W2 can attend to W1, also W3, and maybe even W4, attend to everything in the future. But in the decoder, you cannot do that because you are supposed to decode. You are not supposed to see the future words in the decoder. So you can only see attend to W1. And if you are doing the W3, calculating the self-attention for W3, you can only look at W1 and W2 and W3 itself. You cannot look at W4. So you need something to mask out this connection to the future layer. So this is called masking. So we are going to add this masking to the decoder layer. So in addition to that, so this is the text for explaining that here. The self-attention layer in decoder prevents the position from attending to the future position. So the masking combined with the fact that output embedding are observed in one position ensure the prediction. So we don't look at the future position, okay? So this is how we define the masking. So it's going to be a matrix that is divided by diagonal. So this is the visualization of the masking. You can see that if you're doing position 3, you don't look at the future position, the purple thing. If you're encoding position 2, you look at 1 and 2 only, you don't look at the future, and so on, right? Okay. So self-attention layer output is going to be maybe like beginning of sentence, or just like the encoder, decoder in machine translation. So let's look at the attention. So if you so let's look at the iPad for attention. So if you remember the formula from previous lab, attention is the multiplication of the query and the key. So this is called the scale dot product attention, because it is also normalized by square root of t, which is the dimension of the hidden size. And then after that, we go through the softmax layer, and then we multiply this with the value w. So what is the key? What is the value? What is the query here, right? So we have two different types of attention in the transformer. The first attention is self-attention. So self-attention is calculating the attention between each words in the sentence itself. So the query is going to be, maybe if you want to calculate the attention for E2 or H2, the query is going to be H2, and then the keys are going to be H1 and H3, right? So H1 and maybe H2 and H3. Okay, so query is H2 here, and query is H2 here. The key are H1 and H1. And so you are going to calculate the dot product between the two. And then you're going to go scale with the D, which is the dimension of the hidden layer here. And then we are going to go through the softmax, and then we will get the probability for the attention. So what is the value here? Value is also the hidden layer for the transformer encoder itself, right? Or decoder itself. So the value is also going to be H. So, so for self-attention, query, key, and value are the output of the previous layer. So the previous layer H1, the previous layer H2, and the previous layer H3. So for encoder decoder attention, query is going to be the previous decoder layer output, just like in neural machine translation lab, we use the previous state of the decoder to query the encoder output, right? So key and value are going to be from the output of the encoder. So this is like the encoder decoder attention is similar to the encoder decoder attention from the machine translation. And for self attention in the decoder, we do not attend to the future position. So we use the masking to mask out the future position. Okay, so how do we get Q, K, and V? So let's say we have some parameter metrics WQ, WK, and WV defined in the model. So what we do is let's say we have input X. We are going, and it contains two words, apple and orange. We are going to multiply input X with WQ, and we are going to get the query for apple and the query for orange. And similarly, we're going to multiply X with WK. So we are going to get the key for apple and key for orange, and so on, the value for apple and orange. So we will get Q, K, and V for these two words. And then we can simply follow this formula, QK over square root G softmax V to calculate the attention. Okay. So that is basically the attention mechanism. So if you are doing the encoder decoder translation, this is going to be the output from the previous layer decoder for these two words. And key is going to be encoder output for these encoder output. And then the value is going to be also encoder output layer. Okay, that's all. So let's go back to the code. So this is just explaining the attention mechanism. We know that already. And this is how to calculate the attention. So just multiplying key and value and so on. So another thing is transformer use multi-head attention. So the attention that I explained to you was just one head. They have multiple copy of this like attention head with different weight value for WQ, WK, and WV. So so this is going to be multi-head attention. So multi-head attention allows the model to jointly attend to information from different representation subspace. So we will have like each head is going to correspond to a different subspace at different position. So so basically attention is going to be which I explain later, and then we will get one attention head based on this, and then we are going to concatenate all the attention head for multiple attention head, and then we're going to multiply with WO, which is the W output layer, a linear layer from here. Okay, to get the output of multi-head attention model. So yeah, this is going to be the implementation for multi-head attention. So it is like just physically doing the for loop through attention layer and then calculating the concatenating the output and then going through a linear layer. And this is for explaining the key value and query information about encoder decoder attention, self-attention layer, and self-attention layer in decoder. So I have already done that. Now, one of the other important information in the transformer is positional encoding. So as we talk about, we talk about how to encode the positional information in the encoder transformer, since we don't have they don't have a sequential sense of the input. So they use this formula for this along each dimension. So let's say your position is maybe like position is 1. So we use this formula, and 2i is going to be the dimension of your positional encoding vector. So let's say, so this is going to, each dimension is going to be a wavelength in a sine function or cosine function. And this allows the model to learn to attend to relative position for any fixed position. So let's see how we calculate this, okay? So to calculate that positional embedding, let's see we have a sentence W that contains W0 to WL, and each W has a 4-dimensional encoding EW. So the dimension of the model, D model, is equal to be 4 in this case, right? So this is, the EW is your normal word embedding encoding. So how do you find the positional encoding? So positional encoding 2i, so if your position for this dimension 0 is going to be I equal to 0, so 2 times I equal 0 is 0. And then position, you can just multiply this as 1 if your word embedding is position 1. And then you do like 2i, so I is 0, so 2i is going to be 0. So this is sine pos over 1000 power 0. And similarly, if your position is in odd number, so 0 2 times is 0 plus 1 is going to be 1, and then it's going to be this, and so on. You keep doing this, like for the number of positional embedding dimension that you have. So each dimension is going to be like 1 sine or cosine output. Okay, so in transformer layer, the dimension of the model is 512. So the I value will be between 0 and 255, and then you are going to do like I0 for these two and I1 for these two, and so on. So this is how we compute the positional encoding. And we also have the implementation for positional encoding here. If your position is even number, dimension is going to be a sine function. If your position is going to be odd number, dimension is going to be a cosine function. And then you're going to output this. So they have below is the visualization for positional dimension of 100 words in visualize this as a sine function and cosine function. So if we look at this dimension 4 is an even dimension, and you can see the wavelength for dimension 4 of these words is going to look like this. And dimension 5 is an odd number dimension, so it looks like a cosine function. So each dimension have different frequency for the wave, as you notice here. So dimension 6 has it looks like this, and it is a sine function because it's an even number dimension. Okay, so now you know about transformer model. Is pretty fast, right? Since you understand about the attention already. So we can make the full model by combining all the components that we defined before. So it contains a multi-held attention, feed-forward layer, positional encoding, and then we can define the encoder decoder layer with a encoder decoder class function that we defined earlier. And the generator is appended to the last layer of the decoder to decode or to generate the output for translation. Okay, so this is the model transformer with encoder decoder architecture. So this is just making the batch for training, so I'm not going to explain that. So this is the training eBot. We ran through the forward loop. We feed the input to the forward loop, get the output, compute the loss, and then that propagate through it, and so on for the epoch. Yeah. So in the transformer optimizer, they use add-on optimizer, and they do something called landing rate, kind of dynamic landing rate. What it does is during the initial state of training, landing rate started with an initial value, and then you slowly increase the landing rate to a starting point. It's called one up. Like, so you slowly linearly increase the landing rate for a few one up stage, and then you decrease it after that stage. So this is the function for defining that landing rate one up in the transformer model. So you can visualize the landing rate here. So the first, let's say your one up set is 5,000. So for the first 5,000 step, your landing rate increases linearly. And then after that, it decreases. Okay. So this is the transformer layer. So let's look at one example. So these are just defining loss functions such as cross entropy loss. And this is defining the decoding for translation. And you are going to learn about greedy decoding and other more sophisticated decoding methods tomorrow. Okay, so we first try to do a copy test. So what it does is you give a string or a sequence to the encoder, and you want the encoder to produce the exact same sequence. So the data in the source sentence and sequence sentences are the same. And we train it for the copy test. And then we test it using the greedy decoder. So we give the input 1, 2, 3, 4, 5, 6, 7, 8, 9 to the copy test model, and then it output the same sequence. So it did pretty well. Another thing is we are going to train the model from German to English translation. So in the original paper, they use a WMT model to train the WMT dataset to train the model to translate German to English. But they use IWSLD dataset, which is much smaller. So I am also not going to go through this because this is just data loading and very easy. Okay. So, and this is an iterator for connecting the, to go through the data. So, yeah, after that, we will begin training the model. If we have pre-trained model, we would just load the IWSLT model and so on. And you can see the translation. So this translation is not really perfect, but we didn't really train it for many epochs. So yeah. So this is like just showing the result from the original paper trained on WMT, English to German translation. So you can see that the transformer perform pretty well. And it got the state-of-the-art performance at that time. So yeah, and this is just a visualization for the self-attention. So let's go back to the previous. So I think for the learning rate one, we are just trying to start with a small learning rate, and then we try to get to warming up position to get to a good learning rate step. And then after we get this warm up step, we are going to reduce the learning rate, because if the learning rate is really large and the model when the model become better, we don't really want to take a huge step for the learning rate. So we don't really want to learn quick anymore. So we reduce the learning rate after this one up step. Okay. So yeah, it's learning rate decay. Yeah. So yeah, this is the transformer model. So during the 15 minutes that we have left, we are going to show you how to use this library called FAIRC to train the machine translation models without needing to care about implementation details. Okay, so this is a library from Facebook, and you can download it using pip install FAIRC. So if you don't have it, you can just remove the comment and install it again, and then you can use these are the packages that are going to be used for calculating the blue score, and then are tokenizing the sentences. So the FAIRC library contains a lot of pre-trained models that are the state of the art from Facebook AI research. So you can just download the pre-trained model from their website. So if you go to FAIRC website on the GitHub, you are going to see the list of pre-trained model. It contains a lot of state-of-the-art models that you can download. So for example, if you want to download the model for WMT, you can click WMT, and then you see like this is an English to German translation model. You can just click download, or you can copy the link address and do the wget to or call to download the model, and then after that you can use it to translate. Okay, so so this is just the pre-processing step that they are showing. So they use something called Moses decoder to do the pre-processing and removing the punctuation, etc., clean the corpus, and so on, and remove like some special characters and stuff, and so on. So you can use this subword NNT model by doing the pip install subword NNT. Okay. And after that, so this is going to be, so this is your input sentence. And after normalization and tokenization, this is going to look like this. So do you notice this at symbol? So the memo is separated into memo, mem, at, mel. So this is called subword. In language, a lot of sentences, a lot of words can be subdivided into subwords that contain the meaningful unit. So it's not necessarily, subword might not necessarily be meaningful, but this is like the most frequent subsequent words, units of the words that is occurring in the corpus. So man might be occurring a lot itself. And so, yeah, and to get the original sentence back from the tokenized subword, we can just remove the add space, and we can get back the original sentence. So FAIRC contains this command called FAIRC interactive, where you can just run this and you can define the model that you downloaded from the website, and you can specify the source language and the target language to translate, and then the bin size, which will be explained tomorrow in what is the bin size to use in the decoding. It will be explained tomorrow. And then after specifying this, you can just do this code command to use this sentence as the input to the interactive. So you can see that the model is loaded. It contains English with the dictionary focus size of this, and the French with the dictionary focus size of this. And then the source sentence is this, and then the translated sentence is going to be this. So you can just download the model from the website, and then you can do interactive, and then you can get the translation. And then just like I said before, to get the original sentence, you can just remove add space. This is the code for removing the add space. And then, yeah, you will get back the original sentence. Okay. So you can also use the FAIRC library to train your own model. To train your own model from scratch using your own data. So, but then to train your own model, you have to do the pre-processing of your data. So FAIRC also take care of that for you. So what it does is it contains a FAIRC pre-process function or command. So you can just use that command, and you can specify the source language and target language. And you can specify the prefix for each file that you have and in the data directory. So train file and text file and value file in the data directory. And then you can specify in a directory to save the pre-processed data after the pre-processing stage. So this is the destination directory, and so on. This is the threshold for frequency of minimum threshold for the frequency of the target word and frequency of the source word. So if a word occurs less than 5 times, we won't really count it in the dictionary or vocabulary. Okay. So if you have you can use FAIRC to, if you have the data for African to English, you can use FAIRC to train it. So you can just specify your data here. You can use source language as African languages and target language as English, and then you can just specify the path for your training data. And this is going to be the pre-processing stage. Okay, so training will be later. So this is, we can look at the pre-processing, what is inside the pre-processed file folder. So it contains the dictionary, and it contains the parallel corpus in from English to French and so on. So, and we can look at the dictionary for the first 5 words in the dictionary. So it's going to be comma, the full start off to, and so on. And this is the German word in the dictionary. So just like I mentioned, it provide a lot of pre-trained model with pre-trained architecture, but you can also specify your own architecture. I will show you later. So to train the model, you can use this FAIRC.train model, and you can specify the pre-trained, a pre-processed folder for the model data, and then you can specify hyperparameters such as the landing rate, the number of tokens to use, what is the criterion for your loss function, so cross entropy loss, blah, 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 and so on. And what kind of landing rate do you want? Do you want a fixed landing rate? Do you want other kind of dynamic landing rate, and so on? additionally, you can identify the architecture that you want to use. Do you want to use a convolution model? This is a convolution model. Or do you want to use a transformer architecture or LSTM architecture? And where do you want to save your model? Okay. So after training the model, your model is going to live in FAIR-seek model checkpoint under convolution model folder. So to use this model to generate the data, you can use FAIR-seek.generate and then specify the path to the model and what is the bin size that you want to use. You do want to remove the BPE, and this is to calculate the blue score. And yeah, and the output log will be stored in our model.out here. So if you look at our model.out, the first 10 line, this is going to show you the model architecture. And if you look at the last 2 lines, this is just going to show you the blue score and so on, how many sentences are translated. So the blue score for this particular model with bin size 1 is going to be 26.3, okay? So this is just showing the example of generating using another pre-trained model downloaded from the website. So similar to the previous one. And the blue score for this model is like 43.12. So you can also write your own model in Transformer FAIR-seek. So what you need to do is you can write your own encoder, you can write your own decoder, and then you can register the model using a FAIR-seek architecture. So the FAIR-seek will recognize the name of your model when you do the FAIR-seek.train. So first, what you need to do is you need to create a model on your own. So because of time constraint, I won't go through in detail. So you first create a model. So we have like simple LSTM.py here. So it consists of a simple LSTM encoder, a simple LSTM decoder. So encoder and decoder are defined on our own. So we are not going to use FAIR-seek architecture. We are going to use our own model. And then we have a simple LSTM model that combines the simple LSTM encoder we defined earlier and simple LSTM model that we defined earlier. And then simple LSTM model is just a combination of encoder and decoder. And we get the model. So for decoding and other things, we can just reuse the model that is already written in FAIR-seek. So the next thing we need to do is we need to register the model architecture so that the command line for FAIR-seek will recognize it. So we use this register model architecture. To do that, we are going to call our model simple LSTM, and this is actually the simple LSTM that we defined earlier. Oops. So this is the tutorial simple LSTM. So when we use this command, it is going to call this tutorial simple LSTM. Okay. So we just created a simple LSTM model on our own, and we have to move it to the FAIR-seek path. So to do that, we want to know where the FAIR-seek is installed in our system. And we do this command to get the path for the FAIR-seek, which is here. And then inside that folder, there's a model folder. So we are going to copy our simple LSTM code to the model folder. And so if we look at the model folder and try to find LSTM, we find these two. This LSTM is the LSTM predefined in FAIR-seek, and this is the LSTM that we just added. Okay, so to train the model, similarly, we can use this command, FAIR-seek.train, and we can specify the architecture as the tutorial simple LSTM that we defined earlier. And then we can run this to train this. So you can specify the hyperparameters and how many epoch to train, what is the learning rate to use on your own. So you don't have to code these. And after training the model, you can go to the path that you save the model. You can load the best checkpoint, and then you can use the phase generate to generate the output into the output log folder. Okay, so this is going to be the, and we can look at the output log. So this is going to be the initial 10 line of the output log that contain the architecture, and it would also contain the translation for sentences later, which I'm not showing here. And if you look at the tail, this is going to show you the blue score and the performance of the model. So you see that this model is not really good, and also the WNT data set is really large, but we only train it for 3 epochs, so it's not really enough to land the WNT corpus. So the performance of the model is really bad. But yeah, if you set the hyperparameter correctly, you are going to get a better score. So if you look at the log file, you can see the output log. So this is the log file. The first few lines of the log file is going to output the architecture of the model and the properties of the model. And this is going to be the translation of the model from English to French. So this is the source sentence, and this is the target sentence, and so on. And this is the target sentence, the original target sentence. And H is the hypothesis, which is the prediction from the model. Okay, so you are going to see that translation there. Yeah, similarly, for the custom model that we built. Oops. Yeah, the output is missing, but it's supposed to look like, it's supposed to look very similar to this. So it's going to, so this is the, yeah. It's supposed to contain a source sentence, the target original sentence, and the hypothesis sentence, which is your model's prediction, okay? So is there any question about this? So that's the end of our lab. And if you have questions, we have like 2 minutes to talk about. So let me know. Thank you. Yeah, if you have further questions, please post on Campus Wire and we will answer that. And sorry if I'm moving too fast because there are a lot to cover.